7.5 is on L'Hopital's rule. Sometimes we call it, or abbreviate really, like that, LHOP. So suppose we have these indeterminate forms for limits. One of them basically approaching a constant and approaching infinity. So suppose you have limit of f of x over g of x as x approaches c, or you could have the limit of f of x over g of x as x approaches infinity, and you end up with indeterminate forms 0 over 0 or infinity over infinity. So if you do that, then we don't know what it is, right? It's indeterminate, is what we say. So we have this cool theorem. I'm going to state the theorem, and then we will eventually prove it. It'll take a little bit, but it's a very powerful theorem to use. They call it rule, so it's L'Hopital's rule. So L'Hopital's rule says this. Suppose f and g are differentiable on AB, the open interval from A to B, containing C, except possibly at C itself. So it's like you're taking a limit, so you don't necessarily have to approach equal to C. So except possibly at C. So if it's differentiable, then we know it's continuous. So this is a more restrictive hypothesis, but it is differentiable. So if f of x over g of x has the indeterminate form, zero over zero or infinity over infinity at C, and if g prime of x does not equal 0, basically for all x not equal to c, we just say for x not equal to c, and that's on the interval, then we have this. We have that the limit of f of x over g of x as x approaches c or infinity is equal to the limit of f prime of x over g prime of x as x approaches c or infinity, provided that they exist. Provided they exist. So you don't apply the chain rule, or quotient rule. You do not apply the quotient rule to this numerator and denominator. You just take its derivative, top and bottom, separately. So it's kind of an interesting result. I mean, you have two functions, and you're dividing by those two functions, And this is saying that those limits are equal. Okay, so we'll show why that is true, although it may not be totally clear at first, but we'll go through the proof at least. It uses some important other theorems. So let's look at some examples first. Okay, so normally on a, the normal way you'll see this in a book is, definition, theorem, proof, and then examples. But I want to show you examples first this time, just to show you how powerful this is. So suppose you have the limit of x squared minus 9 over x minus 3 as x approaches, well, anything but 3 will be, wouldn't be matter. So normally what we do so far, so this is without L'Hopital's rule. What you would do is factor, right? You do the limit, and you factor that, x plus 3, x minus 3 over x minus 3 as x approaches 3. And then you can see that these will reduce, and that'll equal 6. All right, so now let's do this with L'Hopital's rule. So what you do is you first check to see that it's an indeterminate form. So, of course, it is. So it has to be those indeterminate forms, 0 over 0 or infinity over infinity. And so then what you do is you check that, and then you say kind of what you're going to do. So this is 0 over 0. So then you tell me you're going to apply L'Hopital's rule. It's just like a little notation in the margins sort of thing. So just tell me it's a L'Hopital's rule. And so what you do is you take this derivative and this derivative. Don't use quotient rule. So this is with L'Hop. And so you get the limit of 2x over 1 as x approaches 3. And that's, of course, equal to 6. So let's check that out. I mean, that's just so slick. Okay, so that's what you can do for these. So then sometimes it's a really nice way of doing this. And they often show you this, if you're taking classes in high school, really early. But to go through it, and I mean, you can just do this, but to build to why you can do this, that's where those proofs are going to come in. But let's practice a few of these first. You may have seen this before, is what I'm saying. If not, of course, it's right here showing you. Okay, so let's look at a typical one that's tough to prove otherwise. So what if you had limit of sine theta over theta? Now, as theta approaches 0. Now, this one has been you can't do it real easily. You do it with geometry and trig, and it becomes kind of tough to do. But this is 0 over 0, so you apply L'Hopital's rule, and it becomes really quick and easy to do. So that's 0 over 0. So then you do L'Hop it. So theta approaches 0. Derivative of sine is cosine. Okay, this isn't writing. So give me 1 second here. Okay. Let's try this again. All right, we are continuing. Derivative of sine is cosine. I'm switching pencils. So that's why I have a backup pencil or stylus. All right, so that's cosine theta over 1. Now you can substitute and take the limit. So that's just 1. As you may have seen, like I don't think because I usually show that in class, but I forget how I did it in this online stuff. But that's one of those special limits you need to know. Okay. So let's try a couple of these. Let's continue. So I'll pause before I start doing it, and then you can try it. So do the limit e to the x plus e to the x negative x minus 2 over 1 minus cosine 2x, and then x is approaching what? Let's see, x is approaching 0. So we substitute in and check. All right, put in 0, 0, and 0. So that's 1 plus 1 minus 2 is 0. So we do get 0 in the numerator. And then cosine 0, 0. So it's 1 minus 0, 0. So it is 0 over 0. And so then we apply L'Hopital's rule. Okay, so when you do the derivative of, so say that limit as x approaches 0, don't ever forget that. And then now take the derivatives. Derivative of e to the x is e to the x. But now the derivative of e to the negative x requires chain rule. So that ends up being negative e to the negative x. And then minus 0. And then that's all over 0. And then derivative of cosine. So derivative of cosine is sine. And then there's a times the chain rule. So there's a 2 in front. So this is 0. And then it's negative. And then negative sine 2x times its derivative, which is 2. Okay, so check that one out. So it's 2 sine of 2x. And so now let's see if we can substitute in. Again, I'm getting 1 minus 1 over, and then substitute in here, and you get 0. So I'm getting 0 over 0 again. So then what do you do? Okay, so I still get 0 over 0. And you basically then can apply L'Hopital's rule to this one, because it's the same indeterminate form. And so we do L-hop. So do the L'Hopital's rule again. Derivative of e to the x is e to the x. And then that's minus minus becomes plus e to the negative x. Derivative of sine is cosine. So you end up getting 4 cosine 2x. Substitute in and you get 1 plus 1, so you get 2 over 4, so you get a half. So this is one of those cases you want to apply L'Hopital's rule twice, and you could just you maybe have to keep going a number of times in applying L'Hopital's rule. Okay, so but the key to it really is that you must get this indeterminate form of 0 over 0. If you get like 0 over infinity, or you get infinity minus infinity, those are not the indeterminate forms we can use. We have to manipulate those to get the proper indeterminate form. Okay, I'm just going to erase all that. Okay. Next example. Next one is this one. The limit of ln x over root x as x approaches infinity. So natural log looks like this. Root x looks like that as well, similar. So what happens? Does it approach 1 or what? So let's take a look. So basically, does one of these grow faster than the other when you approach infinity? Say like significantly faster than the other is what it's approaching. So when you do this, you get infinity over infinity. So this is the other case, right? So then you apply L'Hopital's rule. So then you get the limit. And so we just talked about these derivatives. So derivative of natural log is 1 over x. So let me say approaches infinity. So you get 1 over x. And then when you do the derivative of root x, you do d dx of that, you're going to get 1/2 x to the negative 1/2, but this will bring it back up. So you get 1/2, and then you have x to the 1/2 up here. And so this one, you probably want to simplify this a little bit before you continue. So what you can do is rewrite this as the limit as x approaches infinity. And so you have basically hold on a second. Oh, this needs to be a 2. That's right. Okay, so this is a 2 because you end up with it looking like this. It's because of this. It's really 1 over x over that, and then the half comes up to the top. Okay, so check that out. So you get 2, which could just factor out. Then you get root x over x, and you may want to rationalize that. And so you get the limit. So I'm just simplifying now. So that's all I'm doing is I'm simplifying the radical. So simplify first. So I'm not taking derivatives or anything yet, or taking the limit. I'm just simplifying. When I do that, I get 2 over root x, and then now that approaches 0. Okay, so you get x over x, those reduce, and then here's 2 over root x. And then this is fixed on top. Denominator is approaching infinity, therefore it approaches 0. And then back here, just to show you, you get 1 over x over 1 over 2 root x. And then that simplifies to 2 root x over x. And then that's what I rationalized to get 2 over root x. So this is all scratchwork stuff to help simplify everything. So there's my, not scratch, of course, it's research. Okay. Let's go over one more. See, we'll do this example next. This is another example, and this is showing what this limit is. So let's take a look at this. This is really cool. So we're going to look at the limit as x approaches infinity of 1 plus 1 over x all raised to the x. Okay. We want to evaluate that limit. you may or may not recognize what that equals. Let's just go through it. It's just not. I won't let you know yet. Okay, so let's evaluate that limit. This is one of those strange ones that like you may interpret this going to 0, so this is just 1, and so you just get 1 to just it times itself a bunch, so it's just equal to 1. So you could argue that this is basically like 1 plus and then 0, and then this is infinity, so it's just like 1 a bunch of times, so it's just 1. Okay, that would be wrong. It ends up not doing that. So this one is a special number that it approaches. So this is what we can do. So we're going to let, oops, I want to get some words in here, use my words. We're going to let y equal this limit x approaches infinity of 1 plus 1 over x raised to the x. And then we are going to basically take the natural log on both sides. So it's basically logarithmic values. Now you have to probably argue that this is positive. You're approaching positive infinity, so all those values are positive. And so the domain of a natural log is positive, so this is all cool to do. So it's worth mentioning. So you do this, and then it's the natural log of this limit as x approaches infinity of the 1 plus 1 over x to the x. Now, since this is one of those log properties, since natural log of x of anything is continuous on its domain, we may pass the log through the limit. That's how you say it, pass the natural log into the limit. So what you then get is the natural log of y equal to the limit of ln of 1 plus 1 over x to the x as x approaches infinity. Now you can apply properties of logarithms and bring this x down. So this is equal to the limit as x approaches infinity of x ln of 1 plus 1 over x. Now in this form, this is the form of the indeterminate form is infinity times 0. So that doesn't help us to apply L'Hopital's rule. We can't do that. But what we can do is take x, we're going to take x and rewrite that as 1 over x. And so by doing that, you get the limit as x approaches infinity of the natural log of 1 plus 1 over x all over 1 over x. And now this is a form we can take L'Hopital's rule because you have 0 over 0. So this is approaching 0. The 1 over x is approaching 0. So natural log of 1 is 0. And then this is approaching 0. So you get 0 over 0. Now we apply L'Hopital's rule and take the derivative. So you may want to do this on the side to check it out, but you get the limit as x approaches infinity. And then you get this derivative is 1 over, so we'll keep everything in the numerator. So it's 1 over all of this times the derivative of what's inside. So double check this, but I don't want to spend too much time on it. So you get negative 1 over x squared is that derivative inside, times 1 over 1 plus 1 over x. So the second part is the natural log, it's derivative. this is its derivative, is 1 over that, and then the derivative of 1 over x is that. The denominator, again, is the same derivative as 1 over x. So this is over negative 1 over x squared. And those, of course, reduce. So this and this are the same thing. And so you get that this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And now, take the limit. This goes to 0, and you get equal to 1. So this limit equals 1. So there is only one number whose natural log, so we basically have ln y is equal to 1. If and only if y is equal to, by definition, e. So that limit, as you may have recognized, this limit is equal to e. You could have said this is e up here. So this is a great example of applying L'Hopital's rule. So now you can see why defining the natural log in the way we did and defining e the way we did allows us to take these limits and prove what those limits are. Okay, now we get to do some proofs. Fun times.